Okay, so this is electron spin resonance, and it is considerably simpler in terms of pulse sequences than what you are used to in NMR, because our electronics struggles with the nanosecond timescales and with the extreme levels of what in our case is microwave pulses. So this double electron-electron resonance is substantially just a glorified spin echo. You take a pair of electrons, you give one an excitation pulse, then an echo pulse, and there's an echo, except there's another electron present in the system. And those of you who did the NMR pulse sequence analysis would know that what this does is refocuses everything in the system except the inter-electron interaction. And then when you are shifting this pulse, you are modulating the inter-electron dipolar coupling in this case. And once you've recorded that, it's a dipolar modulation between the two electrons. And as you know, it is a function of distance, an inverse cubic function. And it is very easy to extract distances out of this. And this is the substance of this DEER technique. And it's used a lot, including by biologists. You can either have native unpaired electrons, for example, manganese ions, or you can create some unpaired electrons. These are tyrosine radicals. Or you can mutate something or chemically modify something to introduce an unpaired electron. And then it is used for distance measurements. And there's plenty of work on the subject. And because these are electrons, we can look a lot further than we would have done for the nuclei, up to about 100 angstroms in practice. Some more applications here. Photosynthesis from Maxi Rössler, who will be speaking later in this conference, various molecular conductors with copper ions and other such things. Once again, biochemistry. This is from Alice Bowen. Again, two radicals or two metals, we can measure distances. And various exotic molecular systems. And it doesn't have to be the same radical. You can measure a distance between a metal and a nitroxide, for example. Fairly long range. This is an established technique, but this is a data processing conference. And so here I come to the problem that is very significant in this area, that is how to process DEER data. Now, if you solve the quantum mechanics for a pair of electrons at a specific distance, you get this horrendous equation. And it's a cosine and a sine and a few more oscillatory things. These are called Fresnel functions. They're slightly decaying oscillations. But what is important is that this is the shape of the dipolar modulation for 2-point electrons at a rigidly fixed distance. But of course, the electrons are never point and distances are never rigid. And we have to take into account, firstly, the fact that distance distributions exist in any biological ensemble. This is what's called a kernel. This is for point electrons. If we have them distributed, we have to do a convolution of some distance probability density with that kernel. Then, of course, our pulses in EPR are never ideal pulses. At most, we ever hit a tiny little fraction of the spectrum. We can never do it perfectly. And so there's also the modulation depth that accounts for these imperfections. There's also finite concentration effects because the electron pair is not isolated. There are other electrons at greater distances. And so there are additional decaying terms with an effective spatial dimension that depends on distribution details of those electrons. Now, all of these complications, they eventually mix up into this terrible expression, where in green you have what biologists want, and that is the distance distribution in that molecular system, buried in many layers of mass. The biggest mass being this convolution integral. You effectively have to reverse the convolution. And then there's this decay, and there's the modulation depth, and there's noise, and this in red is what you are actually measuring. And this entire crocodile is called Fredholm integral equation of the second kind, and it is singularly unpleasant. Now, the reason why it is unpleasant is that the problem of pulling the distance distribution out is unstable and ill-posed in the mathematical sense. And what do we mean by that? A well-posed problem in the Hadamard sense in mathematics is when a solution exists. Well, thankfully, in our case, it does. When a solution is unique, and in our case, it isn't. There are many slightly broken and noisy solutions which produce the same measurable data in the end. And the solution has to be continuous with respect to the inputs, and unfortunately, it isn't because it's not unique. And then a well-conditioned problem is additionally when the derivatives of the solutions with respect to the various parameters of the equation are small. And of course, for the same reason, if it's not continuous, then of course it cannot be differentiable. So it is not well-conditioned and it is not well-posed. And here's an example from catalysis. This is a gold nanoparticle functionalized with linkers, so sulfur groups attaching to it, and then linkers containing unpaired electrons here. And we have an analytical solution for this nanoparticle. It is supposed to be a sharp peak, so at 20 angstroms, the most probable distance, and then a smooth pedestal. And as you can see, the standard solvers, at least those that were around in 2008, they mess up this pedestal, and this is the consequence of that instability and ill-posedness, and it is really a thorny problem. There are many decades of work that went into relevant problems across physics. Okay, so one band-aid is what's called a regularization. You say we know that these distance distributions are kind of smooth, so we do the least squares solution to that horrible equation, and we additionally demand that the norm of the derivative be small. And of course, if the solution is smooth, then the derivative is small. And if the solution is rough, then the derivative is big. And so this extra term penalizes rough solutions, smoothes them out, and it's called Tikhonov regularization. And or you can just fit a model, if you have one, a bunch of Gaussians in the simplest case. Now, the common feature of these approaches is a great number of rather difficult adjustable parameters. As a friendly postdoc from the nearby lab pointed out, one obscure adjustable parameter is too many. So we need to find ways of solving this without introducing unnecessary fudge factors like this alpha here, the Tikhonov regularization coefficient. But ultimately, as you can see, this is a noisy and distorted deconvolution problem. And of course, image recognition is also a deconvolution problem. You have some doggedness kernel, and you're trying to deconvolve a picture of a dog to get a delta function where the dog has been. And machine learning is a possibility. And to our amazement, when we tried it, it worked better than it should, as you will see. But another round of introductions is perhaps in order here. So you're all biologists. I don't need to tell you how a neuron works. It collects action potentials, depolarization waves that arrive on the dendrites and then passes a depolarization wave down the axon. The mathematical model is very, very similar. A bunch of numbers arrive. They are assigned weights. They are collected into a sum. There's an extra term called bias, which is how ready that neuron had been to fire, and then a nonlinear activation function, usually a sigmoid, and then a number pops out. And it's really an almost trivial function. Take a bunch of inputs, weigh them, sum them up, add a number, and pass it through a sigmoidal function, and that's it. The beautiful thing about it is a theorem that was proven in 1989. For any arithmetical or logical function, and for any finite accuracy, there exists a finite network of such things that outputs that function to that accuracy. Networks of such neurons are universal approximators. And that is a fairly extraordinary fact, partly explaining perhaps why you and I are neural networks rather than Turing machines. Okay, so this is not new. Machine learning has been around in NMR since the early 90s. There have been proposals to do nuclear chemical shift prediction in 1992. Our very own Jim Prestegard, NMR spectroscopists would know who that is, in 1997 tried quite successfully applying neural networks to structure determination for secondary structure from some NMR data. The biggest problem around that time has been that the available computing power to really make that work had been insufficient by, to my estimate, about 9 orders of magnitude. So it has taken the ensuing 25 years to bridge those 9 orders of magnitude, and now these things really work, as you can plainly see on the BBC. So they were on the right track, they just didn't have a powerful enough computer. And these days, NVIDIA really changed the game. This card costs more than my car. It's 10 to the 13th multiplications per second. This is an extraordinary number. Anyway, and there will be a talk later today from Gogulan about one other successful application of these things. Anyway, Now, the biggest problem with this is, of course, there's not enough Deer data in the world, and there will never be to train something like this. You need billions of data pairs to train a neural network. But we wrote Spinach, right? A high-performance simulation package, so we can try and train them on simulations if we model everything that can go wrong, all the noise, all the distortions, all the phases, and so on. And so what we can do is in our simulations, and there's 10 to the 10 instances of that, we create distance distributions of realistic structural ensembles. We run 10 to the 10 simulations, add all the complications associated with real instruments, and we train a neural net. And then when an experiment arrives, we send it through the neural net and hopefully get our distance distribution out. Now, Jake pointed out when we started all of that effectively this creates an infinite training database and actually removes the under-training problem because the amount of synthetic data you can generate is unlimited. I would point out here that training a neural network is trivially easy. It's a glorified least squares problem. The principal problem all over the machine learning is finding enough training data. And here, thankfully, because we can simulate magnetic resonance so well by now, that is not a problem. Okay, so what is that neural network? It's a standard vector input, so that oscillation goes in. Fully connected layer, basically a matrix vector multiplication. Batch normalization layer, it's a sort of statistical crutch to accelerate convergence. Asymptotically linear, non-linearity here, asymptotically linear because it has to be. These are things related to Fourier and Laplace transform. Normalization because the output is probability density, and then just the least squares, including situations where the data is sparsely sampled because Deer is sampled in an indirect dimension of a two-dimensional experiment. And so initially, quite quickly, we realized that this works. The data, much of the data came from Gunnar Jeschke and from Luis in ETH. And yes, we could reproduce reasonably the experimental data and the known right answers for them. We engaged a few more people, Daniela Goldfarb's group at Weizmann Institute and Enrica Bordignon's group in Ruhr. And look at this. So that is that pedestal that I was talking about at the very beginning. The neural network got it right. Those of you who have done Tikhonov regularization would appreciate that it's actually impossible, mathematically impossible, to get a sharp peak on a broad pedestal from a Tikhonov regularization reconstruction. So the network outperformed the state of the art. Then multiple peaks are not a problem. This used to be a problem because this transform, it's closer to inverse Laplace transforms than it is to Fourier transform. And as you know, inverse Laplace transform is quite a messy thing to do. Then the network somehow learned, we didn't teach it, but it learned to ignore common artifacts. These are so-called running echoes. And you can see the backwards reconstruction just cuts straight through it. We are still figuring out how on earth it learned to recognize these artifacts because we didn't teach it, but apparently it did. And then in situations where the data doesn't contain any data, it is possible to design networks that actually can detect that and reject such data. And you do statistical analysis, but by training, let's say, 100 independent networks on 100 independent databases, and then look at the extent to which they agree. If your input data doesn't contain any information, the networks will all disagree. If the data is well constrained, then the networks will all agree. So the measure of disagreement in an ensemble of neural networks is a measure of statistical certainty here. Okay, so that all work that was all released and published went all the way to PNAS, and the biologists are happily using it. So happy, in fact, they've almost abandoned a few other simulation tools. Now, the biologists are happy, but we are not. We are mathematicians. And to us, this was a problem because a neural network is an absolute black box. And if you look into the eyes of these two gentlemen, they're looking at us with a sort of reproach. This is René Descartes and Karl Popper, the two fathers of objectivism. So, sorry, it's not objectivism, scientific, empirical rationalism. That's what they had invented. And our networks fly in the face of empirical rationalism because they don't have interpretability and they don't therefore have trust. So mathematically, you see, those intermediate layers in the neural network, they are defined up to a permutation. So effectively, the information inside is encrypted. And we had to design a pretty serious mathematical procedure to find out how to look inside and to descramble that. Okay, so fasten your seatbelts. There's a lot of mathematics coming your way now. So a neural net is a vector in times a matrix through a function times a matrix through a function times a matrix through a function. That's all there is to it. If we supply an array of data, it's matrix in, matrix out. And then we assume that some kind of operator exists that we can insert times its inverse that clarifies to a competent human what goes on in the intermediate signaling of that neural network. And that operator would be the minimum or a maximum of some interpretability functional. And we don't know what that is. Okay, we thought, fine, we've got a couple of gazillion signals that go in and go through. And if you look at the intermediate linkages, it looks like not. The assumption had been that if the entire 10 to the 10th intermediate signals are made simultaneously smooth by some transformation, then maybe they're going to be made simultaneously interpreted. At least, you know, it's not an unreasonable thing to assume. And at least we could mathematically formalize that. And if you look at this transformation carefully, you see, it's expected to be linear and differentiable because linear combinations of signals must be descrambled consistently. It is supposed to be invertible because information cannot be lost. And it is supposed to be multiplicative because such is the structure of this network. And stuff that is linear, differentiable, invertible, and multiplicative has a name. It's called a Lie group. And if you've been doing spin physics for as long as we have, you know everything about Lie groups because SU2 is the group that describes the spin physics. Okay, so we didn't pick up SU2, we picked up SO and R. This should be an R over the real field in here, some kind of fonts problem. And tried to find such a transformation as would descramble our neural network. I will not go into this. This is matrix-valued derivative of that descrambling functional that emphasizes the smoothness. That's a chunk of neural network. That's our descrambler. That's the derivative operator, and that's the Frobenius norm. I don't think you were taught how to differentiate scalar by a matrix, but it can be done. And you get this interpretation quality gradient, and you know what to do with the gradient. You plonk it down in optimization method, and you optimize. And then, of course, smoothness is only one possible such criterion. We could descramble on something else. We took the simplest possible DEERNet, 2 layers. It still worked pretty well, even with the 2 layers, and just programmed that in MATLAB. We are talking a couple of 100,000 dimensional optimization here, so you need a serious GPU for that. So that's the entry layer of the network, the weight matrix in it. As you can see, the immediate appearance is utterly obscure. One dimension is ordered because this is time. This is our trace coming in, but the other dimension is scrambled. Once we apply the descrambler, some kind of structure emerges, some kind of interlocking waves. Well, okay, we expect the network to do some digital signal processing, probably in the frequency domain. And so we Fourier transformed both dimensions. And then look at what came out. This is the Fourier transform. So you can see there are frequencies that the network multiplies by 0. There are frequencies that the network multiplies by 0 here. So large positive and negative frequencies are eliminated. And then interestingly, a 0 frequency is also eliminated. It's a notch filter. So it's a bandpass and a notch. Why would the network do that? Well, a notch filter is to eliminate the baseline, because the baseline is the signal of the 0 frequency. Then the bandpass, of course, eliminates the noise. What is that strange feedback that I keep hearing? Okay, fine. Okay, so it has invented a pretty sophisticated digital filter all by itself. And if you zoom in here, this strange hourglass pattern, it's actually a cubic curve. And if you overlay the cubic curve, it's nearly perfect. And why would it want to take the cubic root of the axis in this case, which is what effectively it is doing? That is because in that horrendous equation I had shown you, the dipole-dipole interaction depends on the cube of the distance. It has figured out how to straighten out the x-axis. Okay, well, not bad, right? So the first layer spontaneously evolved after 10 minutes of unattended training a bandpass filter to get rid of the noise, a notch filter to get rid of the line, a frequency axis rectifier, recognizing the fact that we've got this 1 over r cubed, and it packed it into a single layer in a transform that's actually linear if you look at it carefully. Not bad. Okay, so what about the second layer of this tiny 2-layer net that we managed to descramble? Once again, the immediate appearance of the weight matrix is obscure. Once you apply the descrambler, some kind of pattern emerges. And when you look at it carefully, it appears to map rapid oscillations into short distances and slow oscillations into long distances, which kind of makes sense. But there's actually more to this matrix that meets the eye. If you do the singular value decomposition here, you realize that the matrix is approximately orthogonal on the left, and the input singular vectors are oscillations. Engineers call this frequency multiplexing. So it has invented a way of passing signals from one layer to the next. And the matrix is also approximately orthogonal on the right. And the singular vectors here are really weird. When we found them, okay, one is a straight line, the other is a tilted straight line, and then there's a wobble, and then there's a wibble wobble, and then there's a wibble wobble wibble. For my sins, I teach all the mathematics at Southampton chemistry, and I turned up after lecture one day and realized that these are Chebyshev polynomials. And if you look at further ones, right, there's quite a few singular values in here, they continue, they keep on going. So somehow, spontaneously, Chebyshev polynomials turned up in the neural network. It invented them, for all we can see. So this output layer spontaneously evolved frequency division multiplexing at the linkage, spectral filtering regularization because it only keeps the largest singular values and ignores the rest. Frequency distance transform in here because what is the output is the distances, and Chebyshev polynomials, for goodness sake. Now, if you are not shocked by now, you really, really should be, because this is unattended training from a random initial guess, and the blasted thing invented half of the mathematics that we teach to chemists, at least in Southampton. Then Jake did a heroic job of descrambling the middle layer in a 3-layer DEERNet. And the middle layer turned out to be even more fascinating. Now, when you do the descrambling, you get that. When you do the Fourier transform, you realize that some distances, so this is within the band pass, the band of the filter, so that is irrelevant. So in here, it keeps some frequencies where they were, so this is the diagonal part, and it swaps around other frequencies. That's the counter diagonal part. So basically, it inverts the phases of some frequencies, but not the others. Why would it want to have an inversion operation in the middle of the neural network? That is because if you look at this definition, right, that's the noiseless, distortionless DEER, it's a convolution. Linearly independent stuff goes in, linearly independent stuff goes out. In some metric, this is an orthogonal transformation. If you look at the structure of the orthogonal group, the ON, it's actually internally discrete. It has two path-connected SON submanifold special orthogonal groups connected by a discrete inversion operation. But neural network training is a continuous optimization process. It cannot jump across discrete disconnects like that. So ON, the full orthogonal group, is SON Kronecker inversion. What the network appears to be doing here is phase rotations. And as far as we can tell, you see, orthogonal group is not path connected because it has a discrete component. But if you take SON, the special orthogonal group, which is path connected, and Kronecker it with a group of phase rotations, both of these are phase connected, but this is a supergroup of the inversion. So that's path connected, that's path connected. And so the cron is path connected. And so the gradient descent at the neural network training stage can actually make its way through. And as soon as it's happy, the whole thing drops back down into the discrete factor in here that we see then in this layer. So it apparently invented group embedding. Now, you need 20 years of particle physics to even recognize what's going on. And so this is mildly shocking to see this coming out of a neural net just spontaneously. And it took us a couple of months to figure out what's going on in there. So the reviewers said, well, okay, you guys, you assume that you figured out how the network works. So it's a bunch of digital filters, a certain type of integral transform. They said, okay, before we publish that, can you please just put together those exact transforms that you are saying the network is doing manually and demonstrate that you get the same answer out. So, okay, we designed a notch filter in MATLAB, digital signal processing toolbox. We designed the soft low pass filter that was there. We emulated that output layer by a regularized pseudo inverse. And indeed, so that is the noisy data that goes in. You can just about see the denoised stuff that passes this filter. Then the baseline is killed by this filter, so you can see the signal without the baseline. And finally, this transform pretty much nails the ground truth that we have on the data. So we could actually replicate the functionality of a neural network. And we learned a bunch of mathematics. We learned a new method from taking a neural network apart. These are the things that we know about. Network still does better than this, so there's something still hidden in there. We don't know, but there you go. Okay, so the summary of this, the data processing problem turned out to be very straightforward. It just worked. You just need 10 to the 10 data instances to get the network trained. The much more interesting part of that was figuring out what exactly goes on inside that neural network. And as far as I can see now, the ability to simulate by Spinach or anything may be turned into ability to interpret data. If you can generate, a couple of billion instances of synthetic experimental data with a couple of billion instances of the right answer, you can train the neural net, which will then be interpreting your real data and be resilient to noise, distortions, and other such things. So this Descrambler group method, that horrendous mathematics that I've shown you, actually works on fully connected nets and opens the black box. Works for SON, likely others. It's same complexity as training, so pretty tough. But if you manage to train the net, you should be able to descramble. Open source, released with Spinach. And the fascinating conclusions is a simple 3-layer fully connected network in 10 minutes of unattended training from a random initial guess has invented sophisticated digital filters, spectral filtering regularization, harmonic to Chebyshev transform, and topological group embedding. Now, as we told Leverhulme Trust, and they gave us the money, this is fascinating and slightly scary. Finally, I should acknowledge a bunch of biological neural networks and a few artificial ones. So the biological ones are the two Jakes, Taj and Steve, who worked with me on this. Thanks a lot to Leverhulme for funding that, and to MassWorks for all the technical support. And then there's one non-human neural network to thank and one Turing machine, and that is DEERNet and Spinach. This is all online. Go to Spinach downloads page. It includes DEERNet 2 as a part of it. And thank you for your attention.